Hi everyone, welcome to tutorial 66 of our introductory Python for image processing tutorial series. I hope now you feel comfortable handling data after watching the past few tutorials on pandas. And in the upcoming tutorials, I plan on introducing the concept of machine learning for data analysis and for image processing in general. Now, to be able to do that, you need to know one more thing, which is data normalization. Now, why is this important for us? Again, this tutorial exactly talks about that and how to actually perform this data normalization in Python. So first of all, we need data normalization because when you work with data, there may be many streams of information coming or associated with your data, and each stream may have different range of values. So the technical definition of data normalization is you're changing the values of your numeric columns, or you're actually changing your numeric values in the data set into a common scale without obviously distorting the differences in the range of the values. Meaning you cannot change the information contained in these values, but you want to bring all the values to a common scale so you can compare it. So for example, if you have a data set that has the age and salary, the age obviously ranges between, let's say, 0 to 100. Well, if it's salary, maybe the age ranges from 18 to 100, but your salary may range anywhere from, I don't know, let's say 1,000 to 1 million, right? So you need to bring everything to a similar scale so you can actually compare, or you can actually train a machine learning algorithm to understand this data. So this is basically what data normalization is. Now, I just mentioned why normalization, because a bunch of machine learning algorithms, deep learning, regular learning, including linear regression and logistic regression, they require data to be scaled. And I'll show you an example later on, but not just these linear regression, logistic, and neural networks, but other approaches, for example, like k-means and support vector machines. If you don't know what these are, please do not worry. The next few tutorials lays the foundation for us to slowly go through one concept at a time, so we learn these how to code these in Python. Okay, so algorithms like k-means and support vector machines, again, we'll talk about these later on. They're also affected by these range in feature values. Now, what do I mean by feature values? For example, if you look at whatever this data set is, okay, let's not worry too much about what this data set is, but one column has the title radius, the other one is texture, perimeter, area, smoothness, a whole bunch of stuff. But here you can see this column is on average has a value about 15, 16. Same thing with this, okay? And the perimeter is around 100s. Area is in the thousands, but then the smoothness value is in a decimal, like tenth of a, let's say 1/10. And then the next few columns are, I guess, 1/10 and 100th. So how do you compare these, or how do you train this? And when you're training a machine learning algorithm, how not to bias it towards the larger values, right? So this is exactly why we need data normalization. Now, in case you aren't convinced yet, let's actually jump into a piece of code so we can quickly check, how the accuracy depends on whether we are normalizing or not normalizing our data. So we're back looking at our Spider IDE for our Python code, and you see a bunch of numbers on the screen. And this is, again, the commented out text describing the data set we're going to work with. And this data set is a breast cancer data set from Wisconsin, and it contains many columns. And the first column is diagnosis, either it's benign or malignant, okay? And all the other columns are features or attributes that we are going to use to train an algorithm to predict the diagnosis, whether it is going to be benign or malignant. Okay, and as you can see, the numbers are ranging from 1820 here to 1000 here and 122. So this is the whole point. Let's actually go ahead and not normalize and look at the result, and normalize and see how it is. So this further reinforces the point that normalization, hopefully, that normalization is very important. So again, this could be a quick pandas exercise here. So let's go ahead and run our libraries, import our libraries. And now let's go ahead and import our breast cancer data set. And again, this data set, I provided the link up here, so you can go ahead and download it, or just do a quick Google search for this. You'll definitely find it. So we already looked at the data, but if you would like to describe it, again, go ahead and describe. I'm transposing this so I get my values. I mean, it comes out in a meaningful way here, okay? So my ID, again, ID doesn't matter, radius, mean, and I have 569 total data points, and the mean value is 1.4. That's great. Texture, the mean value is 1.9. They're in the same scale. Perimeter is 10 times compared to radius and texture. And the area and smoothness, well, area is 100 times. You see, it's 10 to the power 2, 100 times compared to the radius. And my smoothness is 1/10 of it, or in fact, yeah, it's about 1/10 of this, and so on. So we know that there is a big range here. So let's go ahead and process this. Again, the typical steps involve, first of all, is there any null data? Because when you're trying to fit a bunch of data to any algorithm, it doesn't know how to handle null data. You either drop it or you either fill it. Again, please watch the tutorial on how to handle null data. So let's go ahead and run this line. It kind of tells us exactly how many null data, and looks like this is a very nice data set with no null data. So we're all set to proceed. The next step, I'm going to rename the column diagnosis as label, because that's more intuitive. It's of course an optional step, but let's go ahead and do it. It's just a minor detail. So now if I go back up, you should see label and not diagnosis, okay? Okay, now let's actually look at how many values do we have as part of our label, and value underscore counts is going to tell me how many different classes I have, and for each of these, how many data points. So I have 357 labeled as benign and 212 labeled as malignant. Okay, so this is how my data is distributed. So now what do we do? Well, in most machine learning algorithms, they do not know how to handle text, right? B and M. Let's change our values into categories. So I'm replacing my B with a value of 1 and M with a value of 2. So again, I'll cover these in the upcoming tutorials, so that message is reinforced. Okay, so now we have our data set ready. So we have a data frame that has 569 data points and 32 columns. Of these 32 columns, the first column labeled label, yeah, is going to be our label, or Y values, the value that we're going to predict for our machine learning. So that's what I defined here. My Y equals to the data frame only with the column labeled label. So, and my X is again the same data frame, except I don't want these two columns, label and ID, because ID doesn't tell anything about the data. It's just an ID. And label again is the labeled data. It's not predicting. It's not part of my attributes. So I'm going to drop these two, and my X is going to be 30 columns, because we dropped two of these. Okay. Now here is where I'm importing a couple of libraries for scaling the data. Okay, again, let's not focus much on that, but I'm going to skip that step for now. Let's skip the normalization part, and let's go ahead and split our data into training and testing. I'll talk about this again later on in many of our upcoming tutorials, but all I'm trying to do here is splitting my input data, X and Y, into, let me create some space so you can see it, into a test size of 20% and training size of 80%, okay? So of all of these 569, 455 belong to my training set and 114 belong to my testing set. Okay, and why do I do that? So I can validate my model on the data that hasn't been used for training, okay? So next step is, let's go ahead and use a machine learning algorithm. In this case, I'm gonna use something called support vector machines, SVM, and from there I'm going to use the linear support vector machine. Okay, so and then I'm going to fit my training data to that model. So this is how easy machine learning is. You pick something and go ahead and fit the data. Okay, and it's already done. It's actually going through 10,000 iterations, and the message I got down here, this is very important. It says convergence warning, liblinear failed to converge. increase the number of iterations. So with this type of data, it did not converge even after 10,000 iterations. Okay, now we can go ahead and make the prediction and go ahead and print the accuracy. Let's print the accuracy. It says 93.8%. That's not bad, even though the problem did not converge. And let's go ahead and print the confusion matrix. Again, I'll explain what these are in a second when we see the result. So the confusion matrix is out of 71 plus 7, I got 7 wrong. That's not bad, actually, even though the problem did not converge. And 71 positives in our test data, 78 positives in our test data. Of those, 71 came out as correctly as positive and 7 came out as negative. Okay, 7 benign and 71, whatever the class 1 is, which is benign, yeah, and 7 as malignant. So in our case, we are mischaracterizing these 7 benign ones as malignant. And the 36 of these they seem to be correctly classified. So our model is not doing bad, even though I didn't scale it. That's because the scale ranges are not that drastically different. If they are like 10,000, 20,000, 30,000 for one column, and then 0.1, 0.2 for other column, you'll see much worse results here, okay? And you can see that the accuracy for no disease is 100% or 1.0, and with lung disease is 91%. Fine. Let's go ahead and normalize the data and see if this gets any better. Okay, so how do we normalize it? There are many ways. Again, please watch the next tutorial where I actually go through different ways of normalizing it. But for now, let me go ahead and just use this min-max scaler. Okay, let's see what it is in the next tutorial. And once I import that, I'm going to scale all my x values. I'm not going to scale my y values because y is prediction, right? It's either 0 or 1 or 2 in our example. So let's go ahead and scale all the parameters that we are using for our machine learning. And then that's it. Now they're all scaled. If I actually open my x values here, you see they all are between 0 and 1, as you can see here. Okay, so all values are scaled between 0 and 1 because I'm using min-max scaler. If I used a different scaler, then the ranges would be different. Again, we'll talk about that in the next tutorial. But let's see how the results look like. So let's go ahead and fit it exactly the same way we did before. And hopefully this time it should converge. It shouldn't say that, yeah, there you go. You see? No warning, no error message, and I got 97.3% accuracy. The last time I believe overall accuracy was 93%. Now let's see how it did for individual classes. Okay, so let's go ahead and print out our confusion matrix, which means out of 70, only 2 are mislabeled. Out of 42, only 1 is mislabeled. And as you can see, our accuracy with lung disease is 97.2, no disease is 97.6. So the overall accuracy went up now, okay? I encourage you to test this out with different types of data sets, whether you're looking at, for example, nuclei shape or mitochondria shape versus some other, comparing your mitochondria shape parameters versus a result that you're looking at. Whatever the case may be, you will work with different range data sets, and some sort of normalization is usually recommended, and sometimes you're forced to do that depending on the type of approach you are actually using. So the type of experiments you can do by yourself, work with different types of data, and also work with different types of algorithms. In this case, we used support vector machines. Go ahead and check how it works out if you use linear regression or random forest or even deep learning. So how does your result get affected if you do normalize or if you don't do normalize? I hope you found this tutorial to be useful. And again, please stay tuned for the next one where we talk about 4 or 5 different ways of doing normalization. Thank you very much.